Hello my dear children, welcome to my channel Sudhir Chemistry. We'll see about to now the SN2 mechanism. What is the SN2 mechanism? SN2 stand for beta substitution nucleophilic bimolecular reactions. And as we know beta, just now we have seen that SN2 will occur more on the primary alkyl halide than the secondary alkyl halide than the tertiary alkyl halide. SN2. So we'll discuss about the SN2 one example here. The example for SN2 means, let us say this is a alkyl halide. We can say this is a primary alkyl halide, but it is treated with the water molecule, and we know water molecule is having a nucleophile like a OH minus, and we are getting here as a CH3OH and H plus from here, Br from here, HBr came off. Means we can say beta 1 degree alkyl halide converted into 1 degree alcohol. To explain this one, we'll go with a mechanism. But as we know that the mechanism for SN2, it occurs only in one step. But it occurs only in one step. How it is one step means where the polarity will get. Let me explain you here. This is a CH3, right? This is a halogen as a Br, and this is a hydrogen, hydrogen and hydrogen. See, but in this case, what is that? Our Br minus is a leaving group, so it develops the polarity between carbon and halogen. It will get partial negative, it will get partial positive. But as it will get the partial positive nucleophile from here, that is OH minus, but it will attack to the carbon atom from the side opposite to the halogen atom leaves. See, halogen is leaving from the right side. Our nucleophile will attack from the left side. Now, this step is a slow step. Slow step is called as a rate determining step. But a rate determining step means it is determining the rate, means I should say rate depends upon the concentration of these alkyl halide. It is taken 1 mole to the power of 1. Even it depends upon the nucleophile to the power of 1. See beta, for SN2 ke liye, what is that? The rate of reaction depends upon the concentration of alkyl halide as well as the concentration of the nucleophile. Is it clear? Rate depends upon the concentration of alkyl halide and concentration of the nucleophile. Means R is equal to, that is a constant K into Rx to the power of 1, and it is a Nu nucleophile to the power of 1. But if you see the order, N is called as a order. Order is the sum of the power of the concentration term. 1 plus 1 is equal to 2. And molecularity, beta, molecularity means number of atoms, ions or molecule participate in the RDS. You can see beta, in this RDS how many molecules are involving. One is a alkyl halide and one is a nucleophile. So how many beta? Two species are involving here in RDS. So the molecularity of this reaction is 2. Achha, when this nucleophile will attack to the carbon, we are getting what? OH, that is making a bond with the carbon, and Br is parting away, and these remaining are the 3 hydrogen as it is. But as we know, carbon valency is 4, but in this case you can see carbon is having how many? 5 bonds. That means this is called as a unstable species, and this unstable species is called as a what? Transition state. These unstable species called as a what beta? Transition state. Then the fast reaction will occur where your nucleophile will leaves and OH is making a bond with the carbon, and we got here as a alcohol. Br minus leaves away. But what is that? We started, your leaving group is from the right side and attacking group is attacking from the left side. And if you see the geometry of these alkyl halide with the alcohol, the geometry is completely inverted geometry we are getting. It was first observed by Walden, and he says this is called as a Walden's inversion. So what is a Walden inversion beta? Whenever the leaving group is leave from the right side and attacking group will be attacked on the left side, the geometry will be completely different. Means suppose I started this compound, means this SN2 reaction will started on the R configuration and the obtained compound will have a S configuration. Then we can say this will be called as a inverted product. It was first observed by Walden, and it gave the name called as a Walden inversion. So better remember here what we discussed till now. Whenever we will perform SN2 mechanism or SN2 reaction, it always gives rise to inverted product. But previously we have seen whenever we are performing SN1 reaction, but it always gives rise to racemic mixtures. Right? Now in all these thing discussion, even this stereochemistry or kinetics we discuss in SN2, same thing we have, we means I didn't say it in the SN, but now I will tell you in SN1. In SN1, what we saw beta? In SN1 we are having a carbocation. Means what is that? In the first case, this is a tertiary alkyl halide. In previous video we saw beta. This is a tertiary alkyl halide. But in this tertiary alkyl halide, in the first step, the formation of carbocation takes place. See, this is the formation of carbocation takes place and halide ion came out. But the formation of carbocation is a slow step. This is a RDS, and for this SN1 RDS is there, means the rate of reaction depends only on the concentration of alkyl halide to the power of 1, because in this slow step we don't have anywhere nucleophile, so rate depend only on the concentration of alkyl halide, but it does not depend upon the nucleophile to the power of 0. Means for SN1, suppose if I will say, if the concentration of nucleophile increases 10 times, what is the rate of the SN1? But it is independent. But if we double the concentration of alkyl halide, rate of SN1 also increases 2 times. If you reduce the concentration of this alkyl halide to the half, then the rate of SN1 also reduces to the half. Come for this case beta, in SN2, if you increase double the concentration of nucleophile, double the concentration of alkyl halide, the rate of SN2 become 4 times, because it depends on concentration of alkyl halide as well as the concentration of nucleophile. But in SN1 case mein, if you double the concentration of nucleophile, double the concentration of alkyl halide, but the rate of SN1 is only increases 2 times, because it depends only on the concentration of alkyl halide. It does not depends on the concentration of nucleophile. Is it clear beta? So this is about the kinetics of the SN1. This is about the kinetics of the SN2. Now remaining part I will discuss. But whenever we will perform the SN1, it will always gives racemic mixture, but SN2 it gives rise to inverted product. Here what we saw beta, in SN1 there is a formation of the reaction intermediate. Formation of reaction intermediate. What is that? You know, that is a carbocation. Carbocation will take place in SN1, but in SN2 beta we are getting a transition state. See beta, this is called as a transition state. This is called as a transition state. Means this is the difference to remember. Transition state obtained in the SN2, but reaction intermediate carbocation was obtained in the SN1, right? Now beta, whatever we discuss in the SN1, SN2, we'll try to solve the question based on SN1 and SN2. Now, but as this SN2 depends upon the leaving group tendency, and if you see the leaving group tendency, iodide will have a more leaving group tendency than that of the bromide, than that of the chloride, than that of the fluoride. Why? Iodine is a larger in size, and larger size of the anion can leave easily, and forming the partial positive charge on the carbon. And wherever it forms the partial positive charge, our nucleophile can attack over it on the side opposite to the leaving group. Hence, SN2 will occur more on Ri than Rbr, then Rcl, then Rf. So our answer should be fourth option. But here, an optically active alkyl halide when allowed to react with a cyanide. Is alkyl halide is optically active, cyanide is a nucleophile. It gives rise to racemic mixture. Do you know beta? Racemic mixture can be given only by the SN1. And SN1 means our alkyl halide mostly should be what? Tertiary alkyl halide. The alkyl halide should be a tertiary. In this case, a dextrorotatory optically active alkyl halide, when it undergoes hydrolysis by SN2, this is SN2 beta, the resulting alcohol is what? SN2 will always be given here as a inverted product. That means dextrorotatory optically active by SN2, it gives rise to what beta? It gives rise to a leviorotatory, because dextro become a levio by SN2, it gives rise to inverted product. The answer should be a second option. Select the correct order of decreasing order of reactivity of SN1 using the order given below. But these, if it goes off, it forms the carbocation, it is a secondary carbocation. Iodine will leave forming the carbocation. This is also secondary carbocation, right? In this case, Br goes off and form, but it is a primary carbocation, and iodine will. See, beta, in this case, the question was given, predict the order of reactivity of the following compound in SN1 and SN2 reactions. See, beta, whatever the alkyl halide they gave, take out the halogen, just get the positive charge. Take out the halogen, get the positive charge. Take out the halogen, get the positive charge. Take out the halogen and get the positive charge. But this is a primary carbocation. This is also a primary carbocation. This is a carbocation bonded with two called as a beta secondary carbocation, and this is a tertiary carbocation. So among all we can say tertiary carbocation is more stable. So D will have a more SN1 than that of a C. But among these two men, if you rearrange it hydrogen from here to here, our 1 degree can be converted into 3 degree, and when you rearrange to here beta, your 1 degree can be converted to 2 degree carbocation. You know, wherever the formation of carbocation is there, always beta rearrangement will be possible for there. And when we rearrange it, our 1 degree become 2 degree, because hydrogen will shift from here 1 to hydride shift, positive charge comes to here beta, it is a 2 degree. This all the part already we discussed in our GOC class. Here beta 1 degree become a 3 degree. So now we can say B will have a more SN1 than that of A. Exactly reverse order for the SN2, because SN2 depends upon what beta crowding. Less the crowding, more the attack of the nucleophile, and more the crowding, less the attack of the nucleophile. Come for these four options now beta. In this case, suppose if Br will goes off, but I will get carbocation, which is a 1 degree carbocation plus it will have resonance. Phenyl group means beta, you know phenyl group can be drawn in this way also. It is having a alternate pi bonds. So pi sigma positive resonance. When it goes off, it forms the carbocation, which is a 2 degree carbocation plus 2 resonance are there. Here resonance, here resonance. But when Br goes off, it forms the carbocation, which is a 2 degree carbocation, right? Plus 1 resonance. But 1 resonance plus this CH3 will have a plus hyperconjugation. But when Br goes off, it will form the 3 degree carbocation plus 2 resonance, 2 resonance plus 1 hyperconjugation, because methyl will show the hyperconjugation here. Now here we can say beta, among all 3 degrees here, so D will have a more SN1 than the remaining 2. But among this 2 degree, check the resonance is 2, resonance is 1. But more the resonance means more the conjugation means more the stability, B. Then it comes as a C, and at last it comes here as a A. It is the order of SN1, right? It is the order of SN1. Exactly reverse order can be seen for the SN2. This is D, then B, then C, and then A is the order of SN2 for the given 4 reactions, right? See here, beta, in the following pair of the halogen compound, which would undergo SN2 reaction faster? Beta, SN2 means what you have to check here? For the SN2, beta, you have to check the crowding. Means when chlorine goes off, it forms the carbocation, and you know it is a secondary carbocation. But when chlorine goes off, it forms the carbocation, but it is a primary carbocation. And we know SN2 will occur on the primary carbocation easily than that of SN2. So among the following, in which pair would the SN2 will reaction occur faster? So I should say here, in this example, cycloalkane having Cl, where SN2 will occur very fast because it is having 1 degree carbocation. But when Cl goes off, it forms the primary carbocation. When iodine goes off, it also forms the primary carbocation. But in this case, what to say here? Ki iodine is having a good leaving group tendency. But a good leaving group, our SN2 will occur easily. Hence, we can say in this case, the iodine may SN2 will occur more easily than this one. That means if we'll talk about this may, among these two, in this case SN1 will occur fast. Among these two, better here SN1, in this case also better your SN1 will occur very fast, because you know for SN1 and SN2 both the reaction depends on what beta, leaving group tendency. So our answer should be for among the two, in this case SN2 will occur fast, and in this case SN1 will occur fast, because leaving group tendency is great for the iodine. Iodine will have a good leaving group tendency than that of Cl. So in this case SN2, SN1 both will occur fast. But it is a 1 degree carbocation, it is a 2 degree carbocation. So among the 1 degree, 2 degree carbocation is more stable. So SN1 will occur in this case easily, and in 1 degree में बेटा SN2 will occur easily. But in the question they are asking SN2 reaction occur faster among the two. So I should say in this compound the SN2 will occur faster. But among these two, SN2 will occur faster in where? So this is the compound where SN2 will reaction occur very faster. So these are the some questions we have seen based on beta SN1 and SN2.